So we're gonna try out to apply some force. Yeah, I was just looking into how to do it. So since we now have functional whoops, let's save that for later actually. In case we ever want to debug. So we'd want to check our collisions with our dynamic objects, and let's see. Let's see. I'm just messing around with something here. Yeah, we will have to fetch our point g vector points, and this method will have to be adjusted because we would like a g vector reference out points, and we will add that to our method here. Since we would like to store whatever points the ray collides with, we of course need to add it, add the point to the vector, and we pass in our point vector so that we can store the data. If the point size is larger than 0, we do some logic. And inside our objects, which handle our physics object, we have some force here. Add force and torque at point object. Yeah. And we pass in the body. And we pass in the point. Point, and we pass in the force, and then we pass in the duration of that time step. And we implement that method. Yeah. Let's see, we have the position in terms of world space, I suspect, which is great. It is the center of mass. Let's see. And we can create a vector where we point relative to center, where we take the math function vector subtract, and we subtract the center of the object, meaning the position, from the point. And then we ask our object to apply add the force and add our current force here. And we, let's see, next we, let me just check what we should do. We should offset by the point. Let's see. We of course add some vector here. Let's see, we have two vectors. Where we have the point and the force. Let's see. The vector product equal to the point. Let's see, the y of the point times the force c minus the point c times the force y. This is the first component. Let's see. Let's see, M120. Yeah, there we go. So this is the first one. This is going to be the second one, which is going to be the C of the point times the X of the force minus the X of the point times the C of the force. And then we do the X of the point times the Y of the force minus the Y. Oh, wait a minute, this is not the Y, this is the Y. And minus the Y times the X. Let me just check this. So Y, C, CY, C, X, XC, X, Y, YC. X. And the last one is going to be like that. This is going to be the vector product. And we simply tell the object that we want to accumulate some torque. And we add the vector product. So yeah, this might work. It may not. Let's see, is it inside physics? Yeah, it must be physics. And we then for const auto reference point in points, we do some stuff. First we have the physics object data. We have the M characters, which we take the first one of, and then the physics object ID. And then we pass in the point, and then we pass in a force. Let's just add some force. Well, we should actually maybe we want to. Oh well, the masses gets applied inside the integration step. So as far as I remember, let's see. And then we do duration, and maybe that's it. Let's see inside our integration step. Yeah, we do mass. So now we, let's see, we have an error somewhere. Let's see. G vector. Oh, no. G vector reference. Oh, wait a minute. Yeah. Let's see if I don't do that, then it works. And now it, oh, wait a minute. There we go. So for instance, if we okay. Let's see. We do not want to limit this. We might want to run it several times. So let's see. Oh well, we might be adding too much force. So yeah. Um, well, the force, of course, needs to be modified by the, let's see, a g vector force, and we have to get math scale vector. Let's see, maybe 10. So instead of that, we do the force here, and we simply calculate for depending on where we shoot from. Yeah, and if the bounding volume actually worked, probably. I mean, at least we can't shoot him out of bounds. Yeah, so as you can see, we yeah, I think we will adjust the force for one. Then we'd like inside the physics simulation here to have a bit less of a bouncy effect. Yeah. So let's see. If I try to, I missed. If I try to aim at the center, yeah. If I try to aim at the feet, if I try to aim at the, yeah, I'm not sure our vector calculation is entirely correct here, but let's just test it a bit more. Let's see if I, yeah, if the bounding box was calculated differently, I actually think we might end up seeing him fall over. Yeah, so that's definitely the next step. But yeah, let's see if I shoot him at the feet. It may be realistically enough. Let's see if we negate the force vector. Let's try to see that. Negate the direction here. Well, then suddenly we do have an opposite effect. That doesn't look very interesting. Let's see. Um, yeah. I just realized that I might be actually also be applying more than one force since I'm shooting too many rays. Yeah, once we get the collider to rotate alongside the object, I think we'd probably have more realistic physics simulations. But it looks pretty funny. And as you can see, I'm just shooting rays here. Wow, that really hit him off angle. Yeah, and I think the bounding volume is calculated from the outer points, meaning that it's not a tight fit. So if I shoot for the corner, he really starts twirling around because it adds a lot of rotational force because I'm shooting like way out here. But nice. And now he bounces a bit off the walls. I kind of accelerated him. All right. Give me just a sec. Well, that's at least one way you can add force to an object. And it doesn't really look realistic since, yeah, the bounding volumes are not calculated properly, meaning that, yeah, the object can't really reorient itself. It's bound to the base of the square box. But once I implement a unbounded, or rather oriented bounding volume instead of an axis aligned bounding volume, uh, everything should be fine. So yeah, I think we started moving in a fun, not boring direction. We got some action. We actually have some basic shooting here. There are a lot of different ways to improve this. Maybe we want some visual feedback or something. But yeah, we're definitely getting somewhere. Yeah. That feels pretty great. It was along the lines of what I hope to achieve. So yeah, we shoot him in the neck and he starts twirling. Let's try to shoot him. Yeah, if we shoot him around the center, you see that we will get more of a push. Uh, yeah, and you can play around with the physics properties of this body. You could give it a different thresholds in terms of acceleration at different parts of the body by using the um, inverse tensor of inertia. We have it defined for this. Let's see here. Maybe we want a bit more here. Let's see. That definitely changes the dynamic, and then if you shoot him in the head, as you can see, he kind of tips over. uh, if only he could fall over, but he can't. Anyway, I think this is kind of what I hope to achieve today. We did a bit of collision checking for rays. It ended up taking forever, but we actually succeeded in creating a bit of interaction and the start of a shooting mechanic. We simply look through the dynamic objects and check if we have an intersection with our ray, and then we calculate the point for it and use that point to apply some physics force to an object. The next thing is to, since we have spheres and since we have AABBs, the last thing is to implement something like, a yeah, oriented bounding volume so that our objects actually can fall over or something to the likes of it. Yeah. So we'll be looking into that in the next episode. I don't know if I'll do it tomorrow or when I'll do it. Yeah, we'll see. But thanks for dropping by. I hope you found some of this interesting, helpful, or something to the likes of it. If you had just least a bit of fun by watching the brilliant physics of this application, feel free to like, comment, or subscribe. Follow on Twitch or YouTube. All right. Thanks for dropping by. Bye bye.